All right, so I realized that this phase, we only pretty much have 2 office hours, but we did technically kind of have an office hour, I don't know, technically fewer full office hours to cover like additional stuff. Reminder that your presentations are a week from today, which I know is kind of short notice. So again, like most important things to focus on are what you're doing your classification for. You don't have to have like your final model results, but if you have a model's results, you can start talking about that as well. And let's say you don't have time to like run your grid search and whatnot. You can definitely start to make conclusions on one of your preliminary models, because in terms of like feature importances, they, for the most part, stay the same. So in case y'all are worried about the short time frame. But it will, I feel like it'll make the timing a little better for phase 4 going into capstones. So for today's office hours, a couple things I want to talk about. First, a very high level conceptual discussion about separability of data and what that means when we're doing classification. And then we're going to talk about EDA, kind of going off of that, as well as SMOTE. So they're all kind of related to the separability of data. So you're going to hear me say this phrase a lot when I'm asking you about your classification project and when we talk about EDA and feature importances as well, because the separability of data is pretty much what determines how well something can be classified, how well a data set can be classified. When I'm saying separability, I literally mean like in the n-dimensional feature space, how possible is it to segment your data into sections? And this is not just for, you know, one specific model. This is kind of the underlying thing of all the classification models we've talked about. So even going from, you know, the tree models where you can look for parts of your feature space to separate and draw segmentation lines in your data set, whether it is SVF, where we literally talked about yesterday, feeding a plane through your data points, or even logistic regression, when you're trying to find some sigmoid curve to fit your data. All of this can really only be done effectively if your data is separable. So to describe with a very simple example, let's just say that my data set looks like this, a bunch of crosses and then a bunch of ticks. This is an obvious example where this data can be separated, right? Crosses over here, ticks over here. In most data sets, it's not that simple, right? You pretty much will always see data that looks something like this, with maybe a little bit of separation, but a lot of overlap. And that's what makes classification hard, because if our data existed in those 2 separate blobs, most models would get 100% classification. But this is what makes it hard. And this is why you can pretty much never achieve 100% testing classification metrics on your data, because of this lack of separation, or relatively less separation in your data. And this does scale up to different dimensions as well, higher number of dimensions. And so when you're doing your EDA, or when you are looking at your data set, exploring it, maybe you're looking at it before you're modeling, maybe you're even looking at it after you're modeling, something to take note of is the separability of data. So this whole concept of your data distributed in space is going to come back in both of the main things I want to talk about today. So in separability of data, one other way to think about it is, let's say you have 2 classes of data. Let's just say you have, let's see what this data set is on breast cancer tumors, and we have 2 classes, malignant and benign. One is good, one is bad, obviously. So what if we had a feature that was the same value for both classes? So for example, okay, I don't know too much about this data set, but let's just say we had a, let's say they were testing for one particular cell. I don't know too much about medicine, but let's just say we are detecting a specific kind of cell within every tumor, and every tumor in this data set has that cell. So that means if we're using a dummy variable, every single row will have the same value. So let me just pull out data.head. Cool. So we'll have another column where the values in that one column all exactly the same. Now, if we just think about that, that feature would be extremely unimportant when it comes to separating the data because there is no variance in that column's values. So that's an extreme example, of course, but this also kind of expands. So let's just say that we have all ones in a column and then one single point zero. And that one single point zero maybe belongs to like the malignant class and the rest are all ones. In that case, just because we have that one variation in the data point, we know that, all right, well, if there's a value of 0 in that column, because only one instance and a malignant instance of the data set has this value of 0, the next time we see a value of 0, we can be pretty sure that it's malignant. Also could be an outlier. It really depends on how you treat your data, but that's kind of where separability of data comes in. Any questions? It's a very abstract concept. And with those examples that I showed, no data will ever look as nice as that. But that's something that we're going to explore a little bit more in this notebook. But any questions about that? All right, cool. So this data set is on, as I mentioned before, breast cancer tumors, and this is all continuous data. So effective EDA for classification, it helps to look for separability of data because that is kind of intuitively what your model is also going to be looking for. It's going to be looking for, all right, what features will allow me to separate my classes better? And so some examples of really effective EDA. So let's just say we're trying to classify whether a tumor is malignant or benign, right? And we have all of this information. This is about the tumor. So all these like measurements of the tumor itself. Yeah, I think these are pretty much all these are all measurements. So let's just say we're taking a look at mean radius. This is an example of a visualization that can be pretty helpful. So let's just say that after we do our modeling, or even before, let's just say that mean radius happens to be an important feature for whether a tumor is malignant or benign. Based on this, this visualization, we can sort of see what the ranges of values are and where that separability might show up within just this one feature. I mean, here we have, 30 different features, but within this one feature, how can we see separability of data? So benign, I think benign means good, right? Benign means that's not harmful, okay. So within the benign tumors, you can see that their radius mainly peaks around like 12, I want to say centimeters, millimeters makes more sense, right? I don't know. It peaks around 12 and it kind of tapers off here. But out of all the malignant tumors, you can see that the mean is maybe around like closer to 17, 18, 19, 20. So this is where you start to see the differences in the distribution of a single feature across your different classes. So a possible thing that you can say when you're trying to make a recommendation or trying to make some, or trying to point out some things where doctors to look out for when diagnosing tumors. Of course, not as a medical expert, but you can say that, all right, well, if it is around maybe this range of values, is a much higher chance of it being benign. But if it is in this range of values, it's much more likely to be malignant. And within this, you can also use your own judgment to talk about some caveats. Maybe around like this region, you should really look at some other features as well. But the fact that you can see that the differences in the distribution of the same feature within the different classes is different, you can use that to quantify some of your recommendations. Does that make sense?
Okay, just for the information. So when you talk about benign, they are like the one which there are tumors, but they don't cause cancer.
Okay.
The ones are the ones which causes cancers, which is more likely to be cancerous.
Okay, thanks, Kishore.
That's the difference.
Yeah, me being, I just take these data sets off a scikit-learn without knowing what they are. But thanks for that. Okay. So this is just an example that's using Plotly. As you all know, I like Plotly because it's interactive, but you can do the same thing with Seaborn as well. This is just, I Googled this example. So this is Seaborn looking at mean radius, and I guess you could also do like the transparent, the alpha, the transparent between the two histograms, but you can see this a little bit more clearly, I think, that, past like 19 millimeters, there are no instances of benign tumors. So everything above 19 in this data, based on this data set, is almost certain to be malignant. using this example. So this kind of EDA, especially when tied together with your feature importances, can be very powerful in making quantitative recommendations. Cool. So what about categorical columns? So this is comparing continuous feature to categorical target. If you have a multi-class problem, you can also do the same thing and you can see where it differs. Oh, and I will also warn you all that it's never going to look this clear cut. I think that this is already relatively a much clearer example, but in a lot of the data sets, especially the ones that are provided, you're not going to see it be so clear cut. And if you do, it's probably because it's very separable and you should expect to see high scores for your metrics. All right, so let's just make up a categorical column because this data set doesn't have any categorical variables. So I'm just going to take the mean area and take the median, and I'm just creating a dummy variable on whether the size of the tumor is above or below the median value, just as an example to have a dummy variable or a categorical variable. So a couple ways you can go about this. Plotly. This is Plotly Express, which is much easier to use, but harder to customize. So therefore, for some reason, it looks like this. But anyways, here we can see the colors determine the target variable. And then these two bars, one is for large area, one is for smaller areas. And just by looking at this comparison, of course, if you have multi-class or multiple values within that one feature, this will expand the same way as well. But based on this, you can sort of see that if the mean area is not large, look how many benign versus malignant tumors there are. And when it is large, there are relatively more malignant tumors. So based on this, if this was a variable that we're using to classify, this might be an important feature because of the differences in the proportion of malignant and benign tumors. Does that make sense? Just because we see that, all right, well, if it's not large, the number of training data points that happen to be benign far outstrips the malignant data points. So you can kind of say, and because your models, no matter what model you're using, kind of will learn this information from your data, you can sort of use this in making your recommendations as well. This is another way to do it. This is with Seaborn. And this is kind of flipping it around. So in this case, instead of having the colors represent the target variable, I'm having the colors represent the different values of the feature. So you can see here, this says malignant benign, but this says area large true false. So it really doesn't, I think it depends on which is easier to visualize when you have, it depends which one has more features, I guess. But play around with your categorical data to see which bar graph is clearer. So in this case, same data, just flipped around. You can see that, all right, if the tumor is benign, a lot more of them are of smaller areas versus larger areas. And if the tumor is malignant, a lot of them are larger areas and a lot fewer are smaller. So you can sort of think of this as conditional probability to some extent. You can say that, all right, if it has a small area, based on our training data, what's the probability of it being malignant? What's the probability of being benign? You could do something like that. And flipped as well. If it is benign, what's the probability that it's a large area? What's the probability that it's a small area? Whichever one suits your business case better, because both of them are kind of factual and just based off of the distribution of your data, you can say whichever one that makes more sense in your business context. Cool. Questions about this? And this EDA, the main keyword I would use to blanket statement all of this kind of EDA is that it's very comparative. And it's comparative between the different classes of your target variable, because that's how you look for separability between your classes. Cool. Any questions about that?
Our EDA should basically center around the target variable and which features are important to that target variable, because at the end of the day, we're just trying to classify if we blindly have some new data, which of the target variables would this fall in, essentially, right?
Yeah, it's definitely a more efficient way of doing EDA. I mean, not all your EDA has to be this way, of course, like your EDA can explore like your correlations, your just your histograms. That's useful information as well, because if you have like a bunch of outliers, that's how you catch those. But yeah, for the most part, if we're talking about like, all right, if I only have time to do like, I don't know, 5 graphs, I would rather you all focus on the comparative EDA.
Thank you.
You're welcome.
So for the graphs, for like the histograms, scatter plots, should we just like focus on, maybe I'm asking a question you already answered, but like, should we just like do a specific feature with our target variable?
So I think there are 2 ways to go about this, and I think it depends on how big your data set is in terms of number of columns. If you have a lot of columns, this can get pretty tedious, and also like you'll just have a lot of graphs to look through. If you find that you do have a lot of columns, I am okay if you do your modeling first, and then based on what the important features are, do these for your important features, so that you don't have like this graph for like 30 columns where you don't need to have it for 30 columns.
So for my data set, if I wanted to, based on my feature importances, I can make histograms and scatter plots for like shot distance and make or miss shots. Is that
appropriate? Yep, absolutely. Because I know we talked about how shot distance happens to be like the most important feature for yours. So maybe yours instead would be like, okay, these are the ones that missed, these are the ones that made it. What are the distribution of shot distance? And then you can actually look at the graph and say, all right, maybe like past a certain distance, are there specific ranges of distances that you have a much higher chance of making a shot versus missing a shot.
All right. Thank you.
You're welcome. Anything else? Because I'm going to move on to talk about dealing with class imbalances next. All right. Okay, so dealing with class imbalances, the separability of your data is still relevant when you're thinking about class balances. So first, we're going to take a look at this data set. You can see that there's a little bit of imbalance. So here we have like a 62 to or 63 to 37% split between a benign and malignant, which is not actually that bad. And also, some people are asking, okay, what is the threshold before I need to do something about my class imbalance? So that's actually a question that I think is really interesting to ask. So let's just say that you have a very, very imbalanced data set. And you have all of these data points over here. And then you have the other class like way out over here. Even if you have like a 99-to-1 split, a lot of models will still be able to classify this perfectly because you have really good separability in your data. You might not even have to do anything about it. Some signs that you do want to do something about your separability, about class imbalance, is if you see that maybe your model is defaulting to always predicting the majority class, which is the tendency of a lot of models to do, to try and optimize for accuracy, for example. Because let's just say I have a 99% green ticks, 1% red crosses. If I just predict everything to be green ticks, I still have a 99% accuracy. I just have very, very low recall, for example. So depending on the context, different metrics matter. But there could be a case where you don't have very much class imbalance, but your points look like this. Then maybe doing some sort of rebalancing technique might help. And it has nothing to do with like the actual like count of the data points. I mean, it does play a part, it does contribute to it as well. But again, with classification, the main goal is to separate your data points. So if you already have good separability, but a very, very strong class imbalance, you might not have to do that. So this is something that I think takes a lot of practice. It also, through EDA, you can figure it out sometimes. But yeah, that's kind of my philosophy on when do you have to rebalance your classes. Questions about that concept?
just one question. Like when we talk about rebalancing methods, right? What would be the main methods that we can use?
Yeah, so I'm going to talk through two methods. One is SMOTE. I'm going to talk through what SMOTE is doing, and another one is called TOMIC links, which we haven't talked about yet, but I'm going to talk about it in a little bit.
Okay.
Cool. Sam, you had a question?
Yeah, I heard what you said and then kind of processed it, but I just want to make sure. Sorry.
Yeah.
So like when you have good separability, like in the first example where you had like 2 red
Mhm.
X's and there's a ton of space and then there's like
Mhm.
30, green X's. So sometimes separability is important, but it's weighted against like the fact that if you need to know when those minority situations come up, that imbalance becomes kind of, you have to just, there's no set rules. That's the thing about data science, which is great, but you kind of have to decide what's more important, separability or the ability to predict based off your
Mhm.
metrics. Okay, cool.
Yeah,
Just want to make sure.
exactly.
Sorry.
No, don't need to apologize. I mainly say that because sometimes people are like, hey, I did SMOTE and then my model didn't do better, what gives? And I'll show you how why sometimes that if you do perform SMOTE and you don't have good separability of your data, SMOTE actually will not really help. So we'll take a look at that next.
Okay, thank you.
You're welcome. Anything else before we start talking about the techniques? Okay. This is just a dummy data set. This data doesn't mean anything. I just want to demonstrate some things about the distribution of your data. So here, I just have two features. I have this blue blob over here, and then a bunch of like scattered orange data points. If you take a look at the counter, actually, let me output. Let me just make sure that I didn't do anything silly. Okay. If I just output counter here, you can see that I have 9,900 blue points and 100 orange points. So heavily imbalanced. So with this, let's see, okay, maybe you can try SMOTE. It looks like there could be some separability in my data because there's this region here that there isn't much overlap. Maybe we lose these points in our classification, but it looks like they're overlapping with the blue anyway. So maybe, I don't know, depends on the context, but it seems like there's some separability. So maybe SMOTE will help. So what does SMOTE do? SMOTE is basically the creation of synthetic data points within your minority class. And there are many different variations on SMOTE. If you actually look at there's an imbalanced learn library that's also very compatible with scikit-learn. SMOTE actually comes from that library. Actually, where is, not this one, but there is, oh, I didn't put the SMOTE documentation here. So you look at SMOTE, which I misspelled. SMOTE IMB Learn. It comes from the IMB Learn library, and there are different kinds of sampling strategies that you can do. But the default is it will resample every class except for the minority class. So if you have multiple classes, so let's just say you have data that's like 60, 40, no, wait, 60, 30, 10. If you use SMOTE by default, it'll up everything from 30 and 10 to 60. That makes sense. It'll just rebalance all your classes basically. And it'll do that by oversampling or creating synthetic data points for the minority classes or any class that isn't the majority. So in this data set, and how do they go about making these synthetic data points? You can't just randomly say like, all right, I'm just gonna throw more orange data points in there and that will be my synthetic data, because that doesn't make any sense, right? Like you need to have some sort of boundaries for where you can create these orange data points. And where SMOTE decides to create these synthetic data points is defined by the orange data points that already exist. So what I'm doing here in this next cell is I'm actually resampling it with SMOTE already. And what this does is, as you can see, the orange data points, no new orange data point exists outside the boundary of the already existing orange data points, if that makes sense. So if I zoom out a little bit, and actually I should have done it in a way that you can see it both side by side, we kind of had this shape already existing. All of these data points fall within the realm of the existing ones. And in this case, it kind of looks like you're taking every point and like you're connecting them with more points. So the points that are being recreated are within the domain of existing data points. So what does that have to do with separability? If, let's just say none of these existed. Let's just say that we're only looking at the data within here. if we're only looking at the data within here, and we're like only connecting these data points, and we're just creating more data points within this range, will that help with the separability of data? Not really, right? Because it's just more points that will overlap with the blue points, more orange points that overlap with the blue points. So in cases like this, SMOTE honestly might not even help. And that's just like, imagine that you have a data set that is very, very difficult to classify. If you ever see those, like I can't think of any off the top of my head, but there's any instance that you can think of that you're trying to tell, okay, is this A or B? And it's very hard to decide. That's what a situation like that is. So anyways, with SMOTE, you're creating these data points within the realm of existing data points, which is why sometimes it works, sometimes it doesn't. I mean, a lot of times it might, because you don't always have like perfect inseparability. So you always have like the ones at the fringe edges that are being able to be classified a little bit better. But yeah, if you have data points that were already just like this and only just like this, there is a chance that SMOTE won't even help. Any questions about that? And like the idea of what we just talked about. All right, so that's SMOTE and why knowing about the separability of your data is important, and also why SMOTE might not help in your imbalance classes. Cool. The other thing I want to talk about briefly is TOMEC links, which is another example, which we have over here. Oh, actually, before I get to that, let's talk about random over and undersampling. So if you have imbalanced data and you have a very, very large data set, another thing you can do is you can just randomly undersample your majority data set. That's a very easy way to go about rebalancing your data. Okay, so next we'll talk about TOMEC links. Let me just remember what's going on here. Oh, okay, I'll talk about this in a little bit. But all right, next we're going to talk about another method called removing TOMEC links. And I don't have that written out in the notebook because I honestly hadn't gotten to it. But let's just imagine we have this kind of data. Let's say we have a lot of green ticks. And then we have a couple red crosses that kind of overlap with our green ticks. And we want to rebalance our classes. Removing TOMEC links is actually something that tries to help with the separability of data. And it does come from the Imbalance Learn library as well. So MB Learn TOMEC links. If you look over here, oh, wait, was that the same thing? I guess this is documentation. The code for that, which I'll walk through in a little bit, is exactly the same as SMOTE, just is kind of doing the opposite. And I'll explain what's happening in removing TOMEC links. So with a data set that looks like this, what removing TOMEC links does is TOMEC links is an undersampling strategy. So what removing TOMEC links does is you look at each minority data point. And for example, let's look at this red X over here. You're going to basically look for the member of the opposing class that is closest to this red X and delete it. So for example, with this X over here, we're going to get rid of this green tick. With this, we're going to get rid of this green tick. We're going to get rid of this green tick, this one, and damn, that one. Let me put that back there. Cool. So with that, you're removing the data points you're moving the majority classes data points that are closest to the minority data points. And because of that, you're trying to create more separability. Some might say this is very selective undersampling, and it does have a tendency to kind of introduce some new biases to your model. But if you really want to see what can help cause separability, TOMEC links is something that does. So that's another strategy that you can try to use as well. It's a little less common, but it is to contrast SMOTE, this is something that will increase the separability of your data, which should make it a little bit easier to classify. Any questions about this method? Sweet. I think I linked this documentation in the guidelines doc, actually, if you are looking for it. But Googling it, you'll find it too. Okay. Let's talk about the implementation of synthetic data and any of these rebalancing techniques with respect to your project. So the main thing to recall here is don't make predictions on synthetic data, which I think as a sentence on its own makes a lot of sense. Why would you make predictions on a fake data point? But in the application of rebalancing techniques in your model, I've seen a lot of students include SMOTE data in their predictions. So what do I mean by this? So we're doing our regular train test split. We take a look at our split. This is a very, very small data set just because I wanted this to run quickly. So we have this imbalance over here. What I'm doing is I am creating a new X train, Y train using SMOTE. So here I'm instantiating an oversampling SMOTE object. I'm going to fit resample my X train and Y train, and note here that I'm not overwriting it. I'm just creating brand new variables for the SMOTE data. And if I do value counts, here you can see that they have upsampled malignant from 162 to 293. So the oversampling has been done here. So in terms of implementation, where do you use your SMOTE data and where do you not? You only use your SMOTE data when you fit your model, because this is the part that is the only part of the process that you need to see the synthetic data. Only in the fit step do you need to see the synthetic data, because this is literally where the model is learning. So as an example, random forest classifier, I fit it on my X train SMOTE and Y train SMOTE. Cool. This step tracks. Next, when we're looking at making predictions, we should not be making predictions on X train SMOTE. You can actually run the code, like if you run X train SMOTE, nothing's gonna break, I believe. Yeah, see, nothing breaks. And if you take a look at these numbers, 293, 162, if I run this, it becomes, oh, hold on, train preds. Oh, this is different. So this will be X train SMOTE. Cool. Oh, never mind. It would be Y train SMOTE as well. There we go, 290, 293. If you're seeing that your confusion matrices have balanced numbers, you're doing it wrong. So anyways, turning this back to X train, Y train. When you SMOTE your data, you're not using any synthetic data in your metric calculation. So just remember here that we're using our original imbalance data to test our model, which doesn't affect our model's performance at all. Because if anything, our model has learned during this fit step, and it has seen our synthetic data to kind of learn these more nuanced patterns of the minority data class. But when you make predictions, it doesn't matter. You should not be doing the SMOTE data. Any questions about that? I know this part can be a little bit confusing. You're not gonna like fail if you don't do it right. I'll just point it out to you, so don't worry. Cool. So yeah, if you are using SMOTE, just make sure that when you see your confusion matrices, and also if you see your classification report, the support line, actually, let me see if I can get that really quickly. Classification report, was it X test, no, Y test, and then Y test preds. And we have to import it real quick. All right. Here, you can see that this support is the imbalance class. But if I do like Y train SMOTE, oh, you technically don't have a Y test SMOTE. Wait, hold on. Yeah, Y train SMOTE, and then you have X train SMOTE like this, and I do train preds. There we go. Yeah, if you're seeing something like this, then you're doing one of the steps wrong. Let me just undo this just in case I forget for the next time. Cool. You can see that this is imbalanced. All right, any questions about that? All right, so all of the stuff that I talked about today is very model agnostic. It doesn't matter which model you're using, which model you're talking about. Every model that we talked about during this whole phase, these concepts of separability apply to those as well. And pretty much it goes that like, if your data is separable, it is easier to be classified. Because if you have like instances where something like this, where you know, if a tumor is always like under 15 millimeters, it's more than likely to be benign. And if it's more than 15, it's more likely to be malignant. If you can see something like this in your graphs, that's probably what your model is seeing as well. And it also doesn't have to be like this as well. It doesn't have to be like, okay, there's one threshold. Something to know, especially if you're using like a tree model, it is possible for it to look like something like this. So let's just say you have, I don't even know what kind of example I would think about, but I have seen this in the past before, where you have one class of data maybe looks like that, and then another class of data looks like that. Then you can say, all right, from this region, it is blue class, but on these outer regions like this and this, it is the orange class. So it doesn't necessarily have to be like one single threshold, but you can say like even different ranges of values that don't even have to be next to each other. Because if you think about it, if you had a decision tree, and I am going down a bit of a rabbit hole, but I think it's interesting to think about. So if I had a decision tree and this is my data, and if I had data points that look like some X's here, some X's here, and then some ticks over here, that's actually very similar to what we're seeing over here, because your decision tree will basically say, all right, let's partition here, partition here. These will be my two, what do you call it? The two branches out of the nodes, whether it's less or more than this value, less or more than this value. So it doesn't have to be a single threshold either. Right. I will also note that these examples are very, very clear cut and simple on purpose. In your data sets, it probably will not look this clean and neat, especially if you don't see good classification metrics. You're really looking for like the parts that have very obvious separation. So for example, let's just see, maybe mean compactness might look a little bit different. Okay, I guess this one doesn't either. But you might have histograms that look very, very close to each other, but maybe your model is really picking up on like the few numbers that are so, like for example, over here, if we don't look at this large lump over there, let's just say that our graph looks like this, is really looking at the really tiny nuances in the distribution of your data, that, okay, if it's above like 0.25 is likely to be malignant, if that makes sense. Also happy to read your graphs for you, or we can read your graphs together if it doesn't make sense either. But yeah, hopefully this was helpful in like giving some intuition on EDA and what kind of data classifies well and what doesn't, and why some techniques help and why some don't. Cool. Any questions? All right. Doesn't have to be about this specific thing. Any project questions that any of you have? I know we just talked yesterday, so not a big deal. There's nothing. I know I'm talking to a bunch of you this week as well.
I have a quick question.
Mhm.
Is it okay for the sake of speed and time to not hypertune some parameters
Yes.
for this project?
Yeah.
Okay.
Yeah, absolutely. I'm not expecting to see like a 500 model grid search. That's not necessary at all. I as long as I can tell that you are hyperparameter tuning, that's fine by me. Oh, and on that note, some might see that you do grid search and your model doesn't perform as well as without grid search. That is actually pretty common, because the defaults are defaults because they tend to perform well. They tend to perform better than the other values anyways. So if you see that your model is not doing better after grid search, that's fine. Just say that your final model is the default parameters. That's absolutely okay as well.
Awesome. I'm actually finding that some of these models are actually like overfitting after grid search. So I'm like rerunning them, trying to make them a little worse, just for the sake of like balancing out the train and test.
Sure. Yeah. Also, I'm not sure if I'm pretty sure I mentioned it at some point. Make sure that you're optimizing for the right metric that you want to optimize for.
Mm-hmm.
So like in grid search, you can set like the default is it will optimize for accuracy, which for imbalanced data is actually not good, because it has a tendency to pick the one that will classify all as majority, for example. Maybe look at switching it to like an F1 score or recall or precision if it depending on the business case.
Gotcha. Thank you.
You're welcome. Anything else? All right. Well, if there's nothing else, y'all have a good rest of your week. Next week, again, as I mentioned, Wednesday is our presentation. So be prepared for that. Again, happy to look at presentation drafts, things like that beforehand. Also on Tuesday, the day before our presentations, I'm going to talk a little bit about productionalizing a model, which means like in the future, if you want to take this project and put it on like a website or something, how you can do that. The notebook is already on the repo here. I'll just pull it up real quick. And we're going to walk through the process of pickling a model, how you can make predictions and scripting your model, because these concepts will feed in nicely to like, if you ever wanted to create a front end for your project, or if you ever wanted to, you can even like play with it in the command line, for example. So we'll talk about this next week. Not necessary for your project, definitely, but useful to know and start keeping in mind.
I had one quick question. Would grid search sort of, would just performing a grid search help with class imbalance, or would you all, like, say you have, you got your results running a grid search and they didn't perform as well as the initial model, should you then perform a class,
Oh, like do SMOTE or something to see whether that will help?
yeah.
Yeah, I think so. There are some models. I think random forests might be one of them. Let me just see real quick. Is it this one? If it's not this one, then never mind. There are some. Let me see. It's called class weight. There we go. Class weight. So there are some models that actually have a built-in. They try and combat class imbalances within the model. So for example, with random forest, because of the bootstrapping that's happening, you can actually tell it to to oversample data points from the minority class. I usually don't recommend this, but this can be a hyperparameter that you do. It does help. I've seen it help in some cases, but what it's doing is just resampling your points, the same data points, to be balanced. I forget if it's like over or undersampling, but they're basically like randomly resampling your existing data. So you can try to combat class imbalance within grid search if the model supports a hyperparameter like this one. But typically this method will be the least effective versus one of the more targeted methods like SMOTE or atomic links. If you see that you have imbalanced data, you run your model, it performs okay. You run grid search, doesn't improve very much. I would say next course of action, and if this is where you are in your project right now, I would say one of two things. You can look at implementing SMOTE and being like, all right, let's see whether SMOTE does anything off the get-go. You don't have to do it in a grid search if you don't want. You don't have to do it in a grid search when you're just testing it out. But also maybe from the models that you have already run, let's say you say that your vanilla model still performed the best, take a look at some of the feature importances, or even look at your data from there. Like if your data isn't, if your like histograms for your data all look the same, then pretty much nothing that you do will improve it by very much, if that makes sense. I know I went on a bunch of tangents within that answer, but was that?
Yeah, that makes sense. Yeah, no, that makes sense.
All right, good to hear.
Thank you.
You're welcome. You're welcome. Any other questions that we've got today? Okay. If there's nothing else, have a good rest of your week, everybody. I'll see you all back here on Tuesday. I'll see the rest of you. We have like one-on-ones scattered throughout the rest of the week as well. Yeah, something to also mention in case you're trying to reach me next week. Next week, I am actually out of office on Thursday and Friday. So I put that on the calendar over there, but it's not going to affect our study groups. So if you're trying to book one-on-ones, and if you have a one-on-one on either of those days, I'm going to have you reschedule it. And I'll talk about it with you all when I see you all before that. All right, well, have a good rest of your week, everybody.
Awesome.
Let me know, Slack me if you need anything. But yeah, excited to see your products next week.
All right, bye. See you Friday.
Bye, everybody.
Bye, everybody.
Everybody,
Thank you.
good night.